Okay. So, the Lagrange multipliers method is to say that this expression is g because it's an expression that has to be equal to 0 to satisfy my constraint. And then I say that the Lagrange function L is equal to f plus lambda g, where lambda is my scalar, it's my Lagrange multiplier. And that would mean that my Lagrange function is x squared minus y squared plus lambda times 2y minus x squared. And then we find the gradient. So the gradient of the Lagrange function would be a vector with 3 entries. The partial with respect to x, the partial with respect to y, and the partial with respect to lambda. And so my partial with respect to x would be 2x minus 2 lambda x. My partial with respect to y would be negative 2y plus 2 lambda. And then my partial with respect to lambda would be 2y minus x squared. So that is the vector. That is the gradient of my Lagrange function. And the idea is to find critical points of my Lagrange function. And a critical point is where the gradient is equal to 0. Or more specifically, the gradient is equal to the 0 vector, which means that all 3 of those entries in the vector are 0, which means that I have a system of equations with 3 equations and 3 unknown variables, x, y, and lambda. And so I can solve that system of equations using substitution. If these were linear equations, I could solve it using Gaussian elimination, but in this case they're nonlinear, and so we're going to use substitution in the case where I have to solve it by hand. And so the first thing I'm going to do is I'm going to solve the first 2 equations for lambda. So my first equation is saying 2x minus 2 lambda x equals 0. If I rearrange that, I can get lambda is equal to 1, yeah. So then my second equation becomes negative 2y plus 2, because lambda is 1, equals 0. And that tells me that y is equal to 1. And if y is equal to 1, then 2 times 1 minus x squared tells me that x is equal to the square root of 2 plus or minus. Okay? So I don't actually care what lambda is. That was just to help me solve the problem. And then for those 2 values of x and that 1 value of y, that gives me 2 critical points of my Lagrange function. And that's when you would plug those values of x and y into your function and determine what the values are. In this case, my function f gives me the value of 1 for both of those, because I showed you that a moment ago. And so those would be the 2 maximum of my function, subject to the constraint. That's how you'd solve it with Lagrange multipliers. And that's the idea. Let's do another one. This might be a better question. It says f is equal to 3x plus y plus 10 and I want to minimize it. In other words, find the minimum. And I'm trying to minimize this subject to what constraint? Subject to x squared times y equals 6. So write the Lagrange function. This is going to be, remember, f plus lambda g. So have that memorized. F plus lambda g. And g is what? Perfect. Yeah, g is going to be x squared times y minus 6. The reason I say minus 6 is because the idea is we're taking my constraint equation and we're rewriting it so that one side of the equation is 0. And then we say, well, g is the bit that is equal to 0, and that's why g is x squared times y minus 6. I think a common mistake that I see with my, I've seen in the past with my business calculus students is they would get this problem and they would just say g equals x squared y, and they would forget to rearrange the equation to set it equal to 0. That's important. Okay, so then my Lagrange function is 3x plus y plus 10 plus lambda times x squared y minus 6. So the gradient of lambda would be a vector with 3 entries. The first entry is the partial with respect to x, so that would be 3 plus 2 lambda xy. Let me know if I make any mistakes in my derivating. Yeah. And then lambda is just the g part. It's lambda times g, so that's an easy partial to take. And then, of course, I'm looking for critical points of the Lagrange function, so I say we're going to set this gradient vector equal to the 0 vector, which gives me a system of 3 equations. I've got 3 unknowns, x, y, and lambda, so I can solve this system by substitution. And the first thing I'm going to think of is taking my first 2 equations and solving them for lambda. So I have the equation 3 plus 2 lambda xy equals 0. Let me rearrange that and solve for lambda. Get lambda equals negative 3 over 2xy. My second equation is 1 plus lambda x squared equals 0. So that means lambda is equal to negative 1 over x squared. And now I can sort of eliminate lambda from the system of equations just by setting these 2 expressions equal to each other. Just set lambda equals lambda. If lambda equals lambda, then negative 3 over 2xy is equal to negative 1 over x squared. So I can cancel out an x. Pretend I multiplied both sides of this equation by x. And then I'll multiply both sides times 2y and multiply both sides times x, and I get negative 3x equals negative 2y. Make them both positive, just for fun. And I can get some kind of formula like y equals 3/2 x. Okay, now let's use the third entry in my gradient vector. So the third equation that I was gifted with is x squared y minus 6 equals 0. And I can say this is like 3/2 x cubed equals 6. Which is like saying x cubed is equal to 4.
Doing the same problem and it just kind of came out like this. Yeah. Also confused how the G method didn't give this.
So what I'm going to do in Desmos is I'm going to make level sets of this f function, which should just be lines, because f is linear. I just have to remember how to do this. So I'm going to make u a vector of constants and then rearrange this to solve for y. So y is going to be equal to negative 3x minus 10 plus u. And then to make a bunch of level sets in Desmos, you can just make u negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. There we go. There we go. So those are the level sets of my f function. Subject to this constraint, x squared y equals 6. Okay? So I'm looking for places where this green curve, my constraint curve, is parallel to the level sets, right? And that means there's like a place right here that looks like it's parallel to the level sets. It doesn't seem like it would be parallel to the level sets anywhere except for this point, okay? So
Plus or minus.
here's a level set that I can move around a little bit. So and try to fine tune it. It only went to intersect in one spot. Okay, maybe I'm being a little bit too picky. Okay, so the x value we found was the cube root of 4. And then the y value we found was 3/2 times the cube root of 4. Okay, so that point, let me make those a different color. That point that we found using the method of Lagrange multipliers, that actually seems to be the place where my constraint curve is parallel to my level sets. Okay? So it seems like the method of Lagrange multipliers gave us the right answer. So here's my function, and I want to maximize this subject to this constraint. Actually, I have two constraint equations. Let's see if this is going to be an issue. So notice that now my function is a function of 3 variables. And again, now I have 2 constraints. What we're going to do in this case is we're going to name a G1 x plus y plus z minus 32. And then we're going to name a G2 x minus y plus z. So now I've got 2 constraints. And so my new Lagrange function is going to be xyz plus lambda 1 times x plus y plus z minus 32 plus lambda 2 x minus y plus z. Okay? Makes sense? You get 2 Lagrange multipliers because we've got 2 constraint equations. But that means my Lagrange function is a function of 5 variables, x, y, z, lambda 1, lambda 2. So the gradient of my Lagrange function is going to be a vector with 5 entries. The entries are going to be the partial with respect to x, the partial with respect to y, the partial with respect to z, the partial with respect to lambda 1, and the partial with respect to lambda 2.
I'm still confused about this variable. I think it should be positive. It's always positive. Yeah.
What?
Okay.
But just, I don't know.
You're entitled to your opinion, even if it's wrong. So the partial with respect to x is going to be yz plus lambda 1 plus lambda 2. The partial with respect to y is going to be xz plus lambda 1 minus lambda 2. The partial with respect to z is going to be xy plus lambda 1 plus lambda 2. The partial with respect to lambda 1 is going to be x plus y plus z minus 32. And the partial with respect to lambda 2 is going to be x minus y plus z. To find the critical points of my Lagrange function, we set this equal to the 0 vector, which is the vector with 5 0 entries. So this gives me a system of 5 equations with 5 unknowns. So we can eventually solve this with a lot of substitution. I think I'm going to solve the first 2 equations for lambda 1. And the first equation would become lambda 1 is equal to negative lambda 2 minus yz. The second equation would be lambda 1 equals positive lambda 2 minus xz. And then if I set lambda 1 equals lambda 1, then I would have negative lambda 2 minus yz equals positive lambda 2 minus xz. I could write xz minus yz equals 2 lambda 2. And so I could factor out a z and write z times x minus y equals 2 lambda 2. And that doesn't immediately solve for anything yet, but it's kind of a convenient way to rearrange things. In fact, I could take the 2 to the other side, and now I have a formula for lambda 2. I've got a formula for lambda 1. I've got a formula for lambda 2. Those things might come in handy eventually. I think the story behind this is that there's not going to be anything that's really hard to do, but this is going to take a long time. Right? So if I look at the last 2 equations, the last 2 equations give me this. I could say equals 32. And then x minus y plus z equals 0. I could add those 2 equations together and get 2x plus 2z equal 32.
True.
Oh.
Yeah, that's true.
Oh. Yeah. So if I subtract, then that's 2y equals 32, so then y just equals 16, right? Yeah, cool. So that's good. That's 1 less unknown, so now we only have 4 unknowns. I haven't used my third equation yet. The xy plus lambda 1 plus lambda 2 equals 0. I could use this definition of lambda 1 maybe. Oh, and heck, remember y is 16. So that's just 16x. 16x plus this definition of lambda 1, which is negative lambda 2 minus 16z plus lambda 2 is equal to 0. So the negative lambda 2 and the plus lambda 2, those go away. I can divide both sides by 16 and say x minus z equals 0, which means that x is equal to z. And if x is equal to z, then this is 4x equals 32, which means x has to be 8, which means z has to be 8. So there we go. We've actually found x, y, and z.